Hello viewers, I am BSSP Rajashekhar, Assistant Professor of Mathematics, Government Degree College for Women, Nalgonda. In today's video, let us do some exercises on coordinate systems. We solve some of the problems on coordinate systems in today's class. Before that, let us quickly recap the definitions and concepts used in coordinate systems. And later we move on to problems on coordinate systems today. First, let us see what are the coordinates of a vector x relative to the basis b, which are called as b coordinates of x. Suppose b is equal to set of b1, b2 and so on bn is a basis for a vector space v, and x is an element of that vector space v. The coordinates of x relative to the basis b are the weights c1, c2 and so on cn, such that x is equal to c1 b1 plus c2 b2 plus so on cn bn. So we know that a basis is a linearly independent set that spans V. In that case, we can say that B is a basis for vector space V. By unique representation theorem, we know that if B is a basis and X is an element of the vector space V, then X can be represented as a linear combination of vectors of V in a unique manner. So those unique weights will be the coordinates of X with respect to basis B, or we can call them as B coordinates of X. So this is what we have defined earlier. So if C1, C2 and so on Cn are B coordinates of X, then the vector in Rn, if these are arranged in a column matrix, then we can call it as coordinate vector of X relative to B. That is denoted by XB, coordinate vector of X relative to B, or we can call it as B coordinate vector of X. So B coordinate vector of X is a column matrix whose entries are the unique weights in the linear combination of X with respect to the basis B. So this is XB, which we call as B coordinate vector of X. The mapping from X to XB is called the coordinate mapping. And when we use a standard basis in place of a basis, then the coordinates of X are equal to coordinates of XE. Usually we denote standard basis by E. For example, the entries in the vector X is equal to 1, 6 are the coordinates of X relative to the standard basis. E is equal to E1, E2. Then 1, 6 can be represented as 1 into 1, 0 plus 6 into 0, 1. So here 1 and 6 are the weights. So this can be represented as 1 E1 plus 6 E2. So our coordinate vector, E coordinate vector is again 1, 6, which is equivalent to this X. So for a standard basis, X and XE, where E is the standard basis, are both equal. And change of coordinate matrix PB is equal to matrix of B1, B2, Bn, where B1, B2, Bn are the vectors of the basis Then the vector equation x is equal to c1 b1 plus c2 b2 and so on cn bn is equivalent to x is equal to pb. This pb is called the change of coordinate matrix from B to standard basis in Rn. So this is the change of coordinate matrix, and left multiplication of PB transforms the coordinate vector xb into x. So x is equal to pbxb. That implies PB inverse x is equal to PB inverse PBXB, that is equal to XB. So PB inverse x is equal to XB. So left multiplication by PB inverse converts x into its B coordinate vector XB. So we can convert x into XB, and similarly we can convert XB into x by suitably multiplying PB and PB inverse. And we have seen that coordinate mapping is 1 1, and it's a linear transformation and non-2. So that is, let B is equal to set of B1, B2 and so on Bn be a basis for a vector space V. Then the coordinate mapping x to xb is a 1 1 linear transformation from V onto Rn. So these are the things we have gone through in the previous classes. In this class, using those concepts, let us solve some of the problems related to coordinate system. And this is the first problem. The set B is equal to set of 1 plus t, 1 plus t square, t plus t square is a basis for P2. Find the coordinate vector of P of t is equal to 6 plus 3t minus t square relative to that basis P. So we know that P2 is a vector space of polynomials of degree at most 2, whose elements will be of the form a0 plus a1t plus a2 t square, where a0, a1 and a2 are real numbers. So here, usually the standard basis of P2 is 1 t square. That is the standard basis. With that standard basis, P of t, the coordinates of P of t will be 6, 3, minus 1. But here, we have a different basis. Instead of standard basis, a different basis B is given to us. We need to find the coordinate vector of P of t with respect to this B. So first, whenever P of t is given and it is to be represented in the form of linear combination of these vectors, we can write in this way. That is C1 V1, C1 B1, B1 is my B1 is 1 plus t. C1 times 1 plus t plus C2 times second vector, that is 1 plus t square, plus C3 times t plus t square is equal to our vector P of t. So now it is in the form of x is equal to C1 B1 plus C2 B2 plus C3 B3, where B1, B2, B3 are the vectors of the basis. So now these C1, C2, C3 are unique, since it is given that 1 plus t square and t plus t square is the basis. We need to find the values of C1, C2 and C3. By equating the like powers of T to find the values of C1, C2, C3, we'll get these three equations. Here, by equating the constant term, we will get C1 plus C2 is equal to 6 here. And similarly, we are equating the terms of T. C1 plus C3 is equal to 3. By equating the T square terms on both sides, we can get C2 plus C3 is equal to minus 1. So these three are the three relations from the above equation. So to solve these equations, let us convert into a matrix equation. So equivalent matrix equation is Ax is equal to D, where A is equal to 110, 101, 011. These are the coefficients of C1, C2, C3. Here we can see it. So the coefficient of C1 is here 1 and 1, C3 is missing. So first row contains 1, 1, 0. 1, 1, 0. Similarly, second row, the coefficient of C1 is 1, the coefficient of C2 is missing, and coefficient of C3 is 1. So 1, 0, 1. Similarly, in the last row, 0, 1, 1. Coefficient of C1 is missing, so it is 0, 1, 1. So here, X, the unknowns, the matrix of unknowns that contains C1, C2, C3. And D is 631. So these values are taken as D. So to solve this equation, let us form an augmented matrix ED. So the entries of D are kept here by adding one more row in this augment matrix. Now we need to convert this matrix into echelon form so that the solutions are simply visible to us directly from this matrix. So by performing elementary row operations, we can convert this equation like this. Here I am making this 0. So R2 goes to R1 minus R2. So 1 minus 1 is 0. 1 minus R2 goes to R2 minus R1. So 1 minus 1 is 0. 0 minus 1 is minus 1. 1 minus 0 is 1. 3 minus 6 is minus 3. The third row is kept as this. Similarly here, using this minus 1, which is a pivot, I am making these two as zeros. So I am adding these two. R1 goes to R1 plus R2. So 1 plus 0 is 1. 1 minus 1 is 0. 0 plus 1 is 1. 6 minus 3 is 3. Second row is as it is. In the third row, also R3 goes to R3 plus R2. We are adding these two. So 0, 1 minus 1 is 0. 1 plus 1 is 2. Minus 1 minus 3 is minus 4. So by performing elementary row operations, this augment matrix AD will become in this form. So that is also can be further converted. Here we have 2, 4 in the last row, 2 minus 4. So by dividing with 2, I'll get 1 and minus 2. And using this one, I can make these two zeros. So again, R1 goes to R1 minus R3. So 3, 1 minus 0 is 1, 0 minus 0, 0, 1 minus 1 is 0, 3 minus of minus 2 is 5. And the second row, we are adding R2 plus R3 gives us R2. So 0 plus 0 is 0, 1 plus 0 is 1, minus 1, 1 is 0, and 3 minus 2 is 1. Third row is kept as this. So now the matrix is in echelon form. So since we have 3 leading entries, all are 1. So now this augment matrix will give us the solution. C1 is 5 and C2 is 1, C3 is minus 2. Now these are very clear from this echelon form. So the coordinate vectors of P of t, which is given in the problem, that is 6 plus 3t minus t square relative to B are 5, 1, minus 2. So this is the way to find coordinate vector of a particular vector of a vector space when the basis is given to us 5, 1, 2. Let us quickly go through it. In this problem, the given vector is to be written as a linear combination of vectors in the basis. We need to find the weights used in that linear combination. So, three equations are formed from that relation, and those three equations are to be solved. For that, we have converted into a matrix form. To solve that, we have taken an augment matrix AD and we converted that into an echelon form. Echelon form gives us the values of weights, that is C1, C2, C3. These are the coordinates, and if those coordinates are arranged in a column vector, column matrix, we can get the B coordinate vector. That is XB, here PB. Here P of t is our vector, given vector. So coordinate vector of the given vector relative to the given basis is 5, 1, minus 2. So this is the problem. Let us move on to one more problem. And here we can observe that A used in this problem is change of coordinate matrix, which is usually denoted by PB from B to standard basis R. That is A is equal to PB here, and D is our vector X. Of course, here it is denoted as P of T. So augment matrix AD is equal to A is PB and D is X, which is equivalent to IXB. So in the problem, we have converted the AD, augment matrix AD, into a form I, and this is I, identity matrix, and these are the coordinate vectors. So IXB form. So it is easy to find coordinate matrix in this manner. So PBX will be our augment matrix, and that is to be converted by using elementary row operations in the form of IXB. So instead of finding PB inverse and left multiplying it, this process is simple. I xb. So the elements which are left after I will be the our required xp. So let us move on to one more problem. Let b1 is equal to 100, b2 is equal to minus 340, b3 is equal to 3 minus 6 3, and x is equal to minus 8 2 3. Show that the set b is equal to b1 b2 b3 is a basis of R3. In the earlier problem it is given that the given set is a basis. Here we have to show that this is a basis first. Later, find the change of coordinate matrix from B to the standard basis. So we need to find PB. Write the equation that relates X in R3 to XB. So we need to write the equation. Finally, we need to find the XB for the given X. So let us first show that the given vectors is a basis. Given that B1, B2, B3 are the vectors, so which are a column matrices. Let B is equal to set of B1, B2, B3, which is also given. So let us form a matrix A with these columns, with these vectors, column vectors. So A is equal to a matrix of B1, B2, B3, which is equal to 1, 0, 0, minus 3, 4, 0, 3, minus 6, 3. So this is our A. Now we can observe that A itself in echelon form. So there is no need to convert this into echelon form in this problem. So A has 3 pivot columns. It is in echelon form, and we can observe that this 1 and 4 and 3. These 3 are pivot positions, and hence these 3 are B1, B2, B3 are pivot columns. And every row contains a pivot position. Since every column is a pivot column, the columns are linearly independent, and every row contains a pivot position. The columns span R3. So since both the conditions of a basis are satisfied, the given vectors form a basis for R3. If in any problem the matrix formed using the vectors is not in echelon form, then we need to convert it into echelon form. And then check whether these two properties are fulfilled or not. Whether the columns are linearly independent. For that, we need to check whether there is any non-pivot column. If all the columns are pivot columns, we can say that the columns are linearly independent. Further, to check whether the vectors span Rn or not. For that, we need to check whether every row contains a pivot position or not. So in this case, both the conditions are satisfied. Every row has a pivot position and every column is a pivot column. So we can say that the given vectors B1, B2, B3 form a basis for R3. So B is equal to B1, B2, B3 is a basis for R3. So first condition is true. Now the second thing is we need to find change of coordinate matrix from B to standard basis. So whenever it is a basis, the matrix formed with these vectors is the change of coordinates matrix. So since B is a basis, its vectors form the change of coordinates matrix. From B to standard basis, it is denoted by EB. So this B is also contains the columns of Rn. It's a column vector. So A itself will be our PB. So then change of matrix PB is equal to 1 0 0 minus 3 4 0 3 minus 6 3. These are nothing but the given vectors. The given vectors are taken as columns of the matrix. And further, we need to give a relation between x and xb. That is what we have seen earlier. X is equal to pbxb. This is the relation between x and xb. So if we left multiply this pb with xb, that is coordinate vector of b of x with respect to b, we will get the vector x. So now we have to find the xb. So x is equal to pbxb, that implies pb inverse x is equal to xb. But we have seen in the previous problem, it is easy to compute xb using this one. pbx is equivalent to ixb instead of finding pb inverse. So let us form the augment matrix pbx. So the entries of x are added to the matrix pb, and using this 4, I am making this 0, since already the entries below this leading entry are 0. So this matrix is in this form. So which can be further converted into these forms by using elementary row operations. After getting this, I am dividing with 4. First row is divided by 4, second row is divided by again 4, and the third row is divided by 1, so that it is in the reduced echelon form. Given this one is itself in echelon form, but we converted it into reduced echelon form so that we can find the values of xb directly. Now, if you compare with this relation, this one is I3. So this is the required identity matrix, and this will be our xb coordinate vector of x. So that we can directly find the values of xb using this method instead of computing pb inverse and multiplying with x. This is a easier method. And let us go through one more problem. The set b is equal to 1 plus t square, t plus t square, 1 plus 2t plus t square is a basis for p2. Find the coordinate vector of p of t is equal to 1 plus 4t plus 7t square relative to b. So this is also similar to the problem which we have gone through earlier. So again, this vector is to be written as a linear combination of these 3 vectors. We need to find these unique weights or scalars C1, C2, C3, which satisfy this relation. From this equation, by equating the like powers of t, You'll get again these three relations. By equating the constant term, you will get C1. There is no constant term here. So C1 plus C3 is equal to 1. And by equating the terms of T, no T term is here. So C2 plus 2C3 is equal to 4. 4 on the RHS. And by equating the terms of T square, C1 plus C2 plus C3 is equal to 7. So these three are the relations. So we need to find the values of C1, C2, C3 such that these three relations are satisfied. So we convert this into a matrix form. Ax is equal to D, where A is the coefficient matrix 1, 0, 1, 0, 1, 2 and 1, 1, 1. These are the coefficients of C1, C2 and C3 in those three relations. Here X is the matrix of unknowns, that is C1, C2, C3, and D is equal to 1, 4, 7. Yeah. So to find the solution for this matrix equation, we form an augment matrix AD by adding the columns of B to A. So now this is AD. Now we need to convert this into reduced echelon form by performing elementary row operations. So these are the elementary row operations. In the second row, it is 0 already. So R3 goes to R3 minus R1. Will give you this matrix. 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 1 is 0 again, 7 minus 1 is 6. And in this one, we are making this 0. R2 minus R2 goes to R2 minus R3. So 1 minus 1 is 0, 2 minus 0 is 2, 4 minus 6 is minus 2. So these 2 minus 2 can be written as 1 and minus 1. And by interchanging the rows R2 and R3, we will get this one. And finally, it is in reduced echelon form. By using this one, we are making this also 0. R1 goes to R1 minus R3. It gives us this final matrix which is in reduced echelon form. So now C1 is 2, C2 is 6 and C3 is equal to minus 1. These are the required weights. So the coordinate vector of P of T is equal to 1 plus 4T plus 7T square relative to B is equal to 2, 6 minus 1. So these are the coordinates of the. This is one more problem. The vectors V1 is equal to 1 minus 3, V2 is equal to 2 minus 8, V3 is equal to minus 3, 7, span R2, but do not form a basis. Find two different ways to express 1, 1. We call a matrix 1, 1 as a linear combination of V1, V2, V3. So here, three vectors are given, which has two entries each. We know that whenever the number of vectors is more than the number of entries, those are not linearly independent. So here, though these three vectors span R2, they are not linearly independent, so they cannot form a basis for R2. If it is a basis, by unique representation theorem, for each vector x in R2, we can find a linear combination in a unique way. But here, 1 is a vector in R2, but this is not a basis. V1, V2, V3 is not a basis. So we can find different linear combinations for this vector x. So here we are asked to find two different ways to express 1 as a linear combination of these three vectors. So let us form a matrix A with the given vectors V1, V2, V3. That is equal to 1 minus 3, 2 minus 8, and minus 3, 7. This is the matrix A, and let U is equal to 1, 1. Let us name it as U. So let C1, C2, C3 be the scalars such that U is equal to C1, V1 plus C2, V2 plus C3, V3. Then we need to find at least two sets of C1, C2, C3. That is the problem. That is the given problem. So we need to solve this and find two sets of C1, C2, C3. For that, let us convert this into a matrix equation. Ax is equal to U, where A is equal to this 1 minus 3, 2 minus 8, minus 3, 7. And X is the matrix of unknowns, C1, C2, C3, and U is equal to 1, 1. Here you can observe that this is a 2 by 3 matrix, which is being multiplied by with a 3 by 1 matrix, and the result is 2 by 1. 2 by 3 is being multiplied by 3 by 1, so your result is 2 by 1. So the augment matrix AU is this one. We are adding the entries of U in the last column. So now we need to convert this into echelon form. For that, we need to make this minus 3 as 0. So R2 goes to R2 plus 3R1. So we are multiplying the first row with 3 and adding to the second row. Then we will get 0 here, and minus 8 plus 6 is minus 2, and 7 plus minus 9 is minus 2, 1 plus 3 is 4. So this is the second column. First, this is the second row. First row is kept as this. And using these two, we can make this 0. Just by simply adding these two, R1 goes to R1 plus R2. So 1 plus 0 is 1, 2 minus 2 is 0, minus 3 minus 2 is minus 5, 1 plus 4 is 5. So here just we are adding R1 and R2 for the first row. And here minus 2, 4 are the entries in the second row. So second row is being divided by minus 2. We will give you this matrix, which is in reduced echelon. Since these two are pivot positions and there are no other entries in those columns other than the pivot positions, remaining are zeros. So this reduced echelon form is equivalent to, if we convert this matrix form into equation form again, which will give you C1 minus 5C3. This is the column for C1, C2, and C3. So C1 minus 5C3 is equal to 5. and C2 plus C3 is equal to minus 2. That implies C1 is equal to 5 plus 5C3, C2 is equal to minus 2 minus C3. So if we write these answers in a column matrix, we'll get C1 is 5 plus 5C3 and C2 is equal to minus 2 minus C3 and C3 is C3. So which can be written as, these are the scalars, 5 and minus 2, here there is no scalar is added to here, that's why it's 0. So 5 minus 2 0 plus C3 times 5 minus 1 and 1. So the vectors are, the scalars which are in this form, where C3 is any real number. So any set of vector in this form, where C3 is a real number, will be a solution for the matrix, and those weights are to be used as a linear combination of given. So for any C3, the above relation gives scalars in the linear combination of U. Let us check. If I take C3 is equal to 0, C3 is 0 and this will vanish. 5 minus 2 0 will be my C1, C2, C3. So C1 is 5, C2 is minus 2, C3 is 0. That is a solution. So let us check it. So U is equal to 1, 1 can be written as 5V1, C1 V1, C1 is 5, so 5V1 minus C2 V2, C2 is minus 2, so minus 2V2 plus 0V3. Let us check it. If we write those V1, V2, V3, we'll get 5 minus 4 and this is 0. 5 minus 4 is 1, minus 15 plus 16 is 1. So this is one of the representation of a linear combination. And if we take C1 is C3 is equal to 1, so here we are substituting 1. So it will be 10, 5 plus 5, 10, and minus 2 minus 1 minus 3 and 1. 10 minus 3, 1. That will be the new set of C1, C2, C3. So our U 1, 1 can be written as 10V1 minus 3V2 plus 1V3. So let us check it again. So 10 times V1 is 1 minus 3, V2 is 2 minus 8, and 1 time minus 3, 7. So 10 minus 6 minus 3, 10 minus 9 is 1, minus 30 plus 24 plus 7, 31 minus 30 is 1. So these two are the two different representations. So now 1, 1 can be represented in this way, 10V1 minus 3V2 plus 1V3, and this is another way. So of course there may be several ways. For each real number, for each scalar C3, you can find a different set, of course, using this relation. So this happened because the given set of vectors is not a basis. So whenever it is not a basis, you can represent a scalar, you can represent a vector with as a linear combination in many ways. So in that case, you can't create a coordinate system, which we have created by using basis. So if we got only a unique representation, then the weights can be converted as a coordinate system. So in this case, we find two sets and many sets. If necessary, many such sets can be determined. Since it is not a basis. If it is a basis, there will be only one way. Those unique vectors will be, those unique scalars will be taken as entries of our coordinate vector, and those weights are called coordinates. This is one more problem. Let H is equal to span of V1, V2 and B is equal to V1, V2. Show that X is in H and find B coordinates of X. So using these two, you have to form this X. So it may not look as easy, but when you convert this into a matrix form and you convert the same into a reduced echelon form, the relations will be very clear. So I'm directly using the echelon form here. So the vectors, the entries in the vectors are taken here. This is my first column and this is my second column and this is my X. Using this one, I'm making these zeros and using this minus 18, the remaining three entries are made zeros. And after simplification, minus 305, minus 3, minus 8, and the remaining are zeros. And if it is converted into reduced echelon form, this will be this one 1 0 minus 5 by 3 0 1 8 by 3. So this is programmed in an Excel file. So these are the results. So from this you can easily see that the system is consistent. System is consistent and the solutions are also clear here. So your C1 is minus 5 by 3 and C2 is 8 by 3. That is, X can be represented as minus 5 by 3 V1 plus 8 by 3 V2. If you perform the same operation, you will get this. So these two are the required scalars. So now I can say that X is in the span of V1, V2 since I can make X using these two. So X is in the span of V1, V2, that is X is in H. And the B coordinates are minus 5 by 3 and 8 by 3 are the B coordinate vector of X. So this is the problem. Let us move on to one more problem. Here three vectors are given in the basis and we are asked to check whether X 4 7 minus 8 3 is in the span of these three vectors. It is a little more complicated than the previous one. So this is also the matrix is formed using these vectors and this is converted into reduced echelon form. This is the final one. So here you will find 3 5 2 and this is also consistent since the last row contains all zeros. So equation is consistent. So 3 5 minus 3 5 2. These are the weights, required weights. So the B coordinates of X are 3 5 2. That is, X can be represented as 3V1 plus 5V2 plus 2V3. So X is in H. So let us go to the Excel lab, I will call it. So those entries are taken here using a program. These are automatically converted into reduced echelon form where you can see. So finally this is in reduced echelon form. These three are the required scalars for coordinates now. So 3 5 2 are the coordinates. So here you can check it if you multiply these things. So minus 6 into 3 plus 8 into 5 plus minus 9 into 2 is 4. Similarly, remaining rows also give these answers. You can see that these two are tallying. So using these scalars 3, 5, 2 in the equation x is equal to 3v1. v1 is this my first vector, and 5v2 and 2v3, you will get the values of x. You can change any value, of course. Here you can see you will get an inconsistent matrix. Here the values are not tallied. Here it is 3, it is some 3 points. But to check why it is inconsistent. So here in this equation we will get here minus 10. So 0 minus 10. So all zeros on the left hand side and minus 10 on the right hand side. So it is inconsistent. In the earlier problem, if you take 8, this system is consistent. So there are all zeros. So these will be discussed in next topic, of course. The rank of this one should be equal to rank of all the matrix. These things will be discussed in the next class. So for this is consistent. These are the values. So we can prepare such programs which automatically give us the values. With this, I am concluding today's class. Thank you for watching.